Hello everyone and welcome to another lesson. Professor Mab here. The topic of today's lesson is three-dimensional principal stresses. This topic is part of the following courses: Machine Element Design and Strength of Materials. In a previous lesson, we discussed how a three-dimensional stress element is described by the following six stress components: sigma x, sigma y, sigma z, tau xy, tau xz, and tau yz. In design problems, an important step is to find the extreme stresses acting on a component that might cause failure. These are called principal stresses. The principal normal stresses occur on a particular orientation of a stress element for which the normal stresses take their extreme values, while all shear stress components are zero. For a three-dimensional stress element, the principal normal stresses can be found by solving the roots of the following cubic equation. In design problems, we rarely need to analyze the three-dimensional stress element, since most maximum stress states occur under plane stress conditions. As we discussed before, the plane stress is a case where all stress components on one surface are zero. The plane stress can be described by the following three components: sigma x, sigma y, and tau xy. An important point about the plane stress is this stress element is still a three-dimensional case, describing the state of stress on a three-dimensional cube, where stresses on one surface are zero. That's the surface facing the screen, and consequently, due to equilibrium, the stresses on opposite surface are zero as well. But the stresses on the other four sides of the cube are not zero and shown in the figure. In a previous lesson, we talked about how we can use stress transformation equations to determine the state of stress at a different set of axes rotated by the angle phi for a plane stress. I'll put that video's link up here so you could watch it later. Using these stress transformation equations, we can find the angles at which the extreme stresses that might cause failure occur. These stresses are also known as principal stresses. The process of finding principal stresses, both normal and shear, is explained in a different lesson. It was done by taking the derivative of the general stress equation with respect to the transformation angle and setting it equal to zero. You can see the resulting equations for principal normal and shear stresses and their associated angles here. More details can be found in another video on my channel. As discussed earlier, the plane stress is still a three-dimensional case describing the state of a stress on a three-dimensional cube where stresses on one surface are zero. So when analyzing the three-dimensional principal stresses for the plane stress scenario, we need to include zero as the third principal stress. By doing so, our three-dimensional principal stresses, sigma 1, sigma 2, and sigma 3, are determined. It is good design practice to sort the three-dimensional principal stresses in the following order. For any plane stress loading, there are three possible scenarios. First, when both sigma A and sigma B are positive. Second, sigma A and sigma B have opposite signs. And third, sigma A and sigma B are both negative. Let's analyze these cases. Let's start with the first case. Both sigma A and sigma B are positive. This means the larger value, for example, sigma A, will be the maximum principal normal stress, sigma 1. Sigma B will be sigma 2, and 0 will be sigma 3. By drawing the Moore's circle, we can visualize the three principal normal stresses. Case 2 is when the sigma A and sigma B have different signs. For example, sigma A is positive and sigma B is negative. In this case, sigma A will be the maximum principal normal stress, sigma 1, 0 will be sigma 2, and sigma B will be the minimum principal normal stress, sigma 3. If we draw the corresponding Moore's circle, we can visualize the principal normal stresses. And finally, the third case when both sigma A and sigma B are negative. This means the maximum principal normal stress, sigma 1, is 0. Sigma A will be sigma 2, and sigma B will be the minimum principal normal stress, sigma 3. By drawing the Moore's circle, we can visualize the three principal normal stresses for this case. Earlier in this lesson, we discussed how we used the stress transformation equations to find the principal shear stresses for plane stress loading. These stresses, tau A and tau B, are described by this equation. They are equal to the radius of the Moore's circle. Considering principal shear stresses occur on planes with 45-degree angle separation, with planes of principal normal stress on the stress element, they will be at 90-degree separation on Moore's circle. Since principal normal stresses occur on the horizontal axis, principal shear stresses will be at 90-degree separation on the top and bottom points of the circle. We can visualize this on the circle drawn here. Now let's investigate the relationship between the principal shear stresses in plane stress and for the three-dimensional loading. We'll do this for the three loading scenarios presented before. The first case, where both sigma A and sigma B are positive, resulted in sigma 1 equals sigma A, sigma 2 equals sigma B, and sigma 3 equals 0. If we draw three circles, one for each pair of principal normal stresses, the radius of each circle is the principal shear stress associated with that plane. For example, let's consider the circle with sigma 1 and sigma 2 that is plotted by a black solid line. This circle has the radius or principal shear stress of tau 1,2, which is equal to sigma 1 minus sigma 2 divided by 2. In a similar fashion, we can find tau 2,3 and tau 1,3. It is obvious that tau 1,3 is the maximum principal shear stress associated with the largest circle. An important note here is tau A and tau B that we found in the plane stress loading do not give us the maximum or minimum principal shear stresses for the three-dimensional loading scenario. Case 2 is when a sigma A and sigma B have different signs. This resulted in a sigma 1 equals sigma A, sigma 2 equals 0, and sigma 3 equals a sigma B. Again, we draw three circles, one for each pair of principal normal stresses. Similar to case 1, the circle with sigma A and sigma B is plotted by a black solid line. Going through all circles, we can determine their radii as tau 1,2, tau 2,3, and tau 1,3. Clearly, tau 1,3 is the maximum principal shear stress associated with the largest circle. Unlike case 1, in this case, tau A and tau B give us the three-dimensional maximum and minimum principal shear stresses. And finally, case 3 is when both sigma A and sigma B are negative. This resulted in sigma 1 equals 0, sigma 2 equals sigma A, and sigma 3 equals sigma B. Similar to previous cases, we draw the three circles. And again, the circle with sigma A and sigma B is plotted in black. Going through all circles, we can determine the principal shear stresses as their radii, tau 1, 2, tau 2, 3, and tau 1, 3. We get the same result that tau 1, 3 is the maximum principal shear stress associated with the largest circle. And last thing, in this loading scenario, tau A and tau B do not give us the three-dimensional maximum and minimum principal shear stresses. Thanks for watching this video. Please let me know if you have any questions.